Hello, here's a nice generic torque balancing example. Torques cause rotation, and so if something's going to be just sitting there in equilibrium, your torques have to cancel. And so here's our formula for torque. Torque is equal to the perpendicular component of the force times the distance it is away from the pivot. So we're going to have to do that for all our different torques. And we can also figure it out with F sine theta times the distance from the pivot, because that'll get us the perpendicular component if this is the angle between the force and the beam. So let's do some figuring. In this case, we've got three forces. We got gravity on the beam, gravity on the mass, and we've got this chord tension. Let's figure out angles first. So we've got an angle between the horizontal and the beam of 35. We can extend the beam if we want, so the angle the chord makes is also 35. Vertical to horizontal is 90 degrees, and 90 minus 35 will give us 55. These will add up to 90. So here's the angle between the vertical and the beam. Here's another angle between the vertical and the beam, so that will also be 55. And here's another angle between the vertical and the beam, so that will be 55 as well. We've got all our angles. At this point, we just do our torque balance. So these two right here, our two gravities, are going to be trying to rotate it counterclockwise. If you imagine this as the center of a clock and this is the minute hand, they're going to be trying to pull that minute hand backwards, whereas this chord is going to try and pull it the normal clockwise way. So two gravities are counterclockwise and the chord is clockwise. Those are the ways they're trying to rotate it. So we'll just do that. We'll say, hey, our torque clockwise equals our torque counterclockwise. Clockwise, we've got our chord. So that is our force of the chord, which is what we're looking for, the tension in the chord. The distance from the pivot that the force is being applied by, given that it is 2.4 meter beam and it is attached right at the end, our distance will be 2.4 meters away. So force times distance, and we're going to need to throw in a little sine 35 to get the perpendicular component of the force. So that is our clockwise component for this chord. And then we got to do the same thing, our F sine theta times d for these other two. So force on the 5 kilogram one would be 5 times 9.8. That gives us the force of gravity on it. If we want to find the perpendicular component, we'll throw in another sine 55 there. Then we've got kind of this guy right here. We'll find that component, or perpendicular component. And we also need the distance from the pivot. Now, if the whole thing is 2.4 meters and we're 0.5 meters from the end, that leaves us with 1.9 meters away from the hinge. So that's our mass here. And then we just got to do gravity on the beam itself. The beam has a mass of 3 kilograms, as it says right here. And we'll do that times 9.8 to get the force of gravity on it. And we'll do another sine 55 to find the perpendicular component of that. And then distance from the pivot, if we got a nice regular object, force of gravity is acting on average in the middle. So we'll just pretend all of it's acting on the middle, because that works great. So if it's acting halfway along a 2.4 meter long beam, that would be at 1.2 meters. And this is it. Torque because of the chord equals torque because of the mass plus torque because of the beam itself. Do some algebra, solve for F chord, and you are done. And that is the end of this video. Hopefully that was helpful.